on a system, we can say, or the most benchmarked heavy code. So let's see. Let's go into towers of Hanoi. So for the first thing we need is the First thing we need is a file. Obviously, the towers of Hanoi file. So that's your simple towers of Hanoi implementation. I commented out the commenting part we don't need, but the main issue that we're trying to solve here is this recursive problem out here. So here it's a very large number of calls for this. So you can see that we have 25 disks in the towers of Hanoi. So that's going to be 2 to the power 25 minus 1 moves. And add to that the recursion, it's going to be a very heavy load. So what we do is, so that's our first step of Python script, what we're going to solve out here. Now, since Medusa is a compiler, right? So what it does is it compiles Python to Dart, a language-to-language trans compiler. So why do we need to compile it again and again, the same file, if we get it once and for all? So we have a caching mechanism for Medusa. So has anyone heard about the HHVM project, Hip Hop Virtual Machine, Facebook's project? Yeah. So has anyone got into it? Like, how does it work? No, right. So the thing about HHVM, apart from running PHP really fast, is its caching mechanism. So I implemented a similar style out here. So for this, and the thing is, it's persistent cache. Unlike other JIT machines like V8 and A, you don't have a persistent cache. Like JVM also doesn't have a persistent cache. The main reason for using a persistent cache is the fact that we want our code to survive restarts, to survive future runs, for anything. It should remember what code it compiled. So for that, I'm using this schema. So this is implemented in SQLite 3 embedded database. So we have our three column layout, so infile, hash, and the gen code. So the infile is basically the absolute part of the file that we're trying to compile. So right now it's hanoi.py, that file. So, and hash is a 256 secure hash algorithm, digest of the contents of the file. And these two columns, mind you, are unique. Why unique? Because so the first time when we're trying to compile, a successful insert happens in a database without any constraint failures. So from that Medusa infers that it has never encountered this file before. So it means that this path is unique and the hash code is also unique. So Medusa is encountering this file for the first time. So for that it initiates a compiler, so which we're gonna see it in a while. So and compiles that into a Dart equivalent Dart code. So we are storing the entire Dart code inside the database. This again inspired from Hip Hop Virtual Machine. So we have the Dart here, and this is persistent. We can use it again and again. So now what happens when we come across the same file from the same path again? So this thing fails, our unique constraint fails out here. So for that, we check the hash, that is the file has been changed or not. If the hash changes, which means the file has been changed, so we need to compile it back again. So if nothing changes, both of them fails, we know that we have it out here. So that way, Medusa can determine that this file has been compiled before, so let's just use that code instead of compiling again. So on this, a bit of metrics, we are saving almost 200 to 250 milliseconds overhead just by using this cache. So this is where all the magic happens, the compiler. So this is completely implemented in Python, a bit of PyPy style, Python that compiles Python to Dart. So it's a bit of bootstrapping that's happening there. So this is how the thing happens. Basically, we start with the source, and you all must be, since we are at PyCon, we know about the AST module. It's a pretty famous module. So the AST module is a very helpful thing that actually provides you with the abstract syntax tree of the code that you just provided it, and also it provides you the visitor pattern for it. A visitor pattern, everyone knows a visitor pattern? out here. Okay, a bit of info. Everyone must be having a bit of idea about the AST, right? It's a tree-like data structure from which you represent your code in a tree-like data structure. For that, you can easy parsing for it. So AST also produce a node visitor framework, so that for that we actually have a callback mechanism. So let's say we want to traverse the AST of a simple 1 plus 1. So for that you have a central node plus with 2 ones on the other side. So every time it visits a number or a operator or anything, so for that you get a callback. So that's the visitor pattern. So everything is provided by the AST module. It's as simple as import AST. So I'm using that, and for every visitor pattern that I visit, for example, I visit a print node, I visit a list node, I visit a dictionary node. So for that, I generate Dart code for each and every node. So basically, I'm going for a top-down traversal. Python uses a top-down parsing, and I generate each Dart code together, and finally I stitch the thing together to get an optimized Dart code. So talking about optimization, optimization happens in various ways in Medusa. For example, you have written 3 functions, but you called only 2 or one of them. You didn't call it actually one. So Python, Medusa will ignore the third code. So the Dart code that Python generates is totally, that Medusa generates is totally optimized, and it's compressed, like in compressed JS code. The Dart code is also compressed and minified as much as possible so that the VM parses it as fast as possible. So let's go into the AST module. This is the AST that's been generated for towers of Hanai code that you just saw. This is not exactly how it generates, but I came up with a graphical view of it to help you understand. So every Python code has a module thing as top code. We all know that. So the first thing that you saw in that code was a function, right? A TOH function. So you can see a function def node being created out there. So the function that this is the name of the function, the parameters, and the body of the function basically. So similarly, there is the entire body, the if, the statements, and the function calls again, and that's the last call function node. Anyone into compilers VM out here? Any weirdos in the crowd who loves DFS, parsers? I don't know, we all hated that thing, right? In our PLT class. So I would be surprised if some hand comes up. Okay, cool. Respect for you. So I'll just go into one of the nodes. I know this is a bit what we Python people don't like, right? Going too much into stuff. But just bear with me, the entire thing should be fine. So this is just the function node. So for that, you just saw that one node being visited out here. So similarly, that's our, this was a Python function that got translated into a Dart function. So here, you can see the main reason for choosing Dart as a endpoint. First things, Dart is very syntactically similar to Python. You can see that. And the major reason is, and the reason why we all love Python is its dynamic typeless nature, right? So we can store anything, everything, do whatever we want. So Dart also has this with a few constraints, limitations, and similarly, and having all these features, Dart is still able to run really fast. So these things kept in mind, so you get the finally translated code. So that's your code. So you might be wondering what all these things are about. The $and wrappings and what the first line means. So creating any let's say compiler or VM or anything that compiles one thing to another language or whatever lower language, you need a runtime for it, right? So for that, the target language, be it assembly code, be it C code, be it Dart, for instance, you need a runtime. A runtime is basically a library of code or function that's going to help run your translated code along with it. It's somewhat like if you attended today's keynote, Kushal was telling about libc, right? So libc is a runtime for C. So all your printf, everything is implemented within libc. So for that we have our Medusa runtime. It's called it's actually an entire folder. I'll show it to you. So this is basically the entire Dart implementation. So here this folder is our runtime. So if you wanna look into it, so this file is a Dart inbuilt a Dart file. This is a pretty huge file. So what you can see, the first thing in this file here is classes, entire classes. So I'm going to show you the one thing. Yeah. So one thing about Python, right? Python behaves weirdly in places. So I'll ask you some code, since we are all good Python programmers. So what do you think is the output of this? 5, right? Okay, cool. Nice one? You sure about it? Right. So any idea what happened out here? Yeah, it is short-circuited. So how are you evaluating this? A list or 5? It's a list, right? So yeah, so that's what something about Python that the other languages don't do generally. So a list, a full list, a blank list is false, mind you, and a blank string is false again. A non-zero value is false. So all that thing, this kind of weird behavior we get in Python. So it helps us along in our code a lot, but it's really a nightmare when you're writing a compiler for Python. So do you know any other language that does this? JS to some extent, right? But not comparing anything. So one quick question, like I have an object of class A and an object of class B. So I'm comparing obj1 is less than obj_b. It compares by the object name, the data type. So if you're comparing an int with a string, so because I comes first than s, so that I is smaller than s, so I is a string. So Python basically compares anything with anything. So that's one really huge headache we had while implementing it. So coming back to this file, so that's another language that supports your proper operator overloading, like your C++. So we are really blessed we got that, so that we are able to implement all this weird behavior using auditorium. So basically this file is the bridge between Python and Dart. So all the functionality that Python has or can do which Dart can't is implemented in this file. So how it's possible, like for example if we take the tuple data type that we have in Python. So for that I created a class called PyTuple. So inside this you'll find all sorts of functions which you might find in the Python file. See PyString, for example, you have functions like capitalize, center. All these things are not there in Dart. So this is basically a wrapper class which has been created over a usual string value out here. So this is the actual internal content, and this is a wrapper class around it. So basically this provides all the functionality that Python can and that can't. It's not yet complete as of now, so it's still being owned. So it's a huge thing. As you can see, it's a very big file, and it's going to go on and on. So this is basically the range implementation, the generator and stuff. So it's a headache to do this file basically. Yeah, so we now saw what the runtime looks like. So this is the final Dart code that's been generated. The $n is basically transforming a normal Dart integer to a Python integer, pyint, so that you can have lots of functionalities and whatever you want. So we can actually see the thing in action. So if I want to see the Dart code, for example, for a file that I have, I want to see what Dart code is generated. So for that, just pass it and pass -c with it. So this is different from that Python here. Do we know what Python does with -c, the normal Python interpreter? Yeah, it runs the command. So I changed it a bit. So I need to work on compatibility. So this thing generates a same name file in .dart, so you can see it. So that's your, if you can make it out, that's a compressed Python Dart code that's been generated. Okay. So you can see all the imports being happening, and the map, that print got mapped to stdout.writeln. So that's a translation that happened, and your Dart is now Python is now into a Dart. So what happens in the background actually, Medusa takes your Python code, breaks it down into an AST, goes through it node by node, optimizes it, and then generates the Dart code for it. So, and the Medusa part is implemented in C++, so it actually forks in between for the compiler to run, and then again forks at the end for the Dart to run. So all that happens with just this click. So mind you, everything happened, the caching happened, everything happened, and you got your output. So you must be all thinking like, what's with the towers of Hanoi? Why did I choose this code? So let's see. So the last part, the prestige, right? This should be good, right? Okay. See, this is, I'm timing the run now. So, how is everyone doing? Cool? Food was good? I hope I'm not boring you on this. Python will be boring you, but I'm not. So that's 9.96 seconds. That's pretty long. The same thing. Let's hope, fingers crossed. Yeah. Cool, and mind you, this was without the cache, so let's try it again. Yeah, so that's the best value that I can get out of it. So you can see nearly a 1500% speed boost. So it's not yet complete Medusa, but you can see that it has potential. It can be growing to infinite levels. So, and if you want to see what all, there's a thing out here. Yeah. So these are the options that you can get with Medusa. So you can actually install your XML Python module, somewhat like the PIP does. So what it does is, it takes your Python module, any file, any .py file, converts it into .precache it, so that you can install and use that file anywhere else. So you can import any other file that you want. You have a help and you have a compile to Dart only switch. So this is it, and I hope that you enjoyed it, and I hope that you contribute to it and make it grow as big as possible. So thank you. And at the end, so yeah, I'm all yours. Yeah.
What about memory management using Medusa? I mean, for example, like Python will do rep counting and PyPy will do like a garbage collection.
So the thing that we avoided all that thing by just compiling it to Dart, right? So that VM takes care of it all.
So it's basically what Dart VM's garbage collection.
Yeah, and it's super fast, believe me.
So how much time will the same TARS of Hanoi take in PyPy for?
PyPy, we tested it. It's around for let's say 3.5 seconds.
So what about C extensions? Can your
right now it's not supporting. It just supports Python extensions. So we are working on the C extensions for it.
It's very cool.
Yeah, thank you.
So, because this is running on V8, ultimately
it's Dart VM. It's
okay.
Yeah.
What are the chances of getting Python to finally run in the browser?
Python,
so you don't have to write JavaScript.
Python already runs in the browser. Like, have you seen this project called Brython? So that compiles Python to JavaScript. So originally we were thinking of going for JavaScript targets for this, but the thing with JavaScript is totally asynchronous. You can't write a simple program like add two numbers and show the result. So that thing won't run in. So what we found out was Dart, and Dart, if you research into Dart, Dart is both server-side, client-side language. So you can have any number of targets with it. So.
Hey, so the example that you showed us, Tower of Hanoi, your implementation, I believe, was tail recursive.
Yeah.
So, and I might be outdated on this, but I thought this was decided that CPython would not have tail recursive optimizations.
Yeah, you want to know why this is happening, right?
So, no, the question is this really fair to compare something which does support tail recursive optimizations as a design decision and something which does not, and then speed ups?
Yeah, my thing is, why should we get out of our comfort zone while doing heavy duty codes? We love Python all, we don't. Yeah, we love Python. So my aim for this is keep doing it in Python. I'll provide you with an abstracted layer which runs faster, that's all. You don't have to a normal user, he or she doesn't have to worry about what's going on inside. It's just that his Python code ran faster, that's all.
Hi. I just wanted to know, how do you handle longs in Python, because there's no limit to the precision in Python for longs.
Longs, that's again that feature that supports the same precision as Python.
Okay, that's okay, fine.
So that's the language we chose, and we are very happy about it.
But you wrote in C++, right?
I didn't get it.
So, okay, fine. How do you do it internally? Like, I just wanted to know, like, maybe.
Yeah, we're just transforming. You saw that wrapper code there, right? The Pynum wrapper.
Yes.
So that thing wraps around the Python data type and creates a Dart data type.
But that you told you wrote in C++, right?
No, this is Dart, right? Python to Dart. There's no C++. C++ is basically the caching and the databasing.
Okay, okay, fine.
The compiler is pure Python.
Compiler is pure Python. Fine.
And anyone else?
So you just showed the speed up on, as you said, a program that could be easily converted into a tail recursive program or not. Is the speed up comparable if you chose a CPU bound purely iterative program rather than something that can be? I mean, is this kind of speed up normal for other CPU bound programs as well?
CPU bound in the sense like you're talking about calculations and stuff, right? So that was kept in mind doing all those things. So Google tried to port that as a general purpose language. So we did try some numeric calculations in it. It was almost fine. The only place where you shouldn't use Medusa is your simple programs, simple calculation, list manipulation, text. So for that, Medusa is not made for those things. Medusa is made for very heavy duty stuff, which we generally go for C extensions or leave Python altogether. So my aim is to use Python there also.
Hi, my question is kind of related to his question. Did you try running this on any benchmark like PyStone or something like that rather than a single program?
Because it just started up, it's a 4-5-month-old project, so we are not really supporting the kind of libraries that they use. So what we ran is pure hard-coded codes. So that's one of the roadmaps. So we will be doing it along with GUI support and stuff. So because it's really nascent stage right now.
Any more questions? Okay.
Does it support Python specific functions like slicing and all those?
Yeah, it's all the basic Python functionality is there. Generators and list. Apart from libraries, everything else is there. So most of the thing you might be finding a bit buggy code here and there because it's still going on. So the SQLite 3 paths that you saw, the table, that I had to change the PPT just before coming out here. So because a commit came today morning, so I had to change that thing. So it's really dynamic right now. And anyone?
Okay. So can we have a huge round of applause for him?
Thank you. And one request, please do commit to it because we are just 3 people. We can't write 1991 worth of code. So we just started 4 months back. So please, we need your contributions for this. Thank you.
Thank you, Rahul. Our next speakers are Mr. Jeffrey and Utkarsh from DreamWorks Animation. Jeffrey is a Jeffrey and Utkarsh both are technical directors of DreamWorks Animation.
Thank you.
this? Yeah, fine. I'll hold this.
Start? It's there. We'll do that, right?
Yeah, let's do that.
Okay. No, we have two speakers. We'll use that. Hello, everyone. Am I audible at the back? No? How about now? All right. Okay. Thank you very much. I know you guys are missing some amazing action in Audi 2 to be here. We really appreciate it. My name is Jeffrey, and I'm joined by my super smart fellow technical director, Utkarsh. We are from DreamWorks Animation. It's a pipeline, something that we built at India for working on movies. So again, we're from DreamWorks Animation. One of the things that we do is make movies, but at its core, DreamWorks Animation has a beating technical heart, and we represent that. So who in here likes Python? Wait, that's not. I mean, who in here likes movies? All right. So everyone likes movies. Cool. I thought we'll start off with, a movie that we just finished. Well, we are finishing working on. It's called Penguins of Madagascar. It's out in November.
Attention! This is Penguins of Madagascar. But what you don't know is they've been leading a double life as secret agents. Their untold story began as four brothers. Are you my family? You don't have a family, and we're all going to die. What? What's the matter with you, Kowalski? Grew up to become masters of disguise, espionage, and aerial assault. Howdy, boys! We're going in hot. No one likes to show off, privates. Now, when it comes to stopping a madman, I have the power to destroy you. They'll have some competition. What the heck is going on?
Remain calm, penguins. You are now under the protection of the North Wind.
We don't even know who the heck you are.
The North Wind is an elite undercover The North Wind is an elite undercover task force dedicated to helping animals help themselves. This November,
You got a soggy madman to stop.
I give the orders around here.
You were supposed to handcuff them, but they don't have hands. They just have flippers, and I have flippers. So it's flipping useless.
The world needs saving.
After them! Hi, boys. It's just like Cuba.
Venice, Rio de Janeiro, Dusseldorf.
We've arrived in the center of Dublin, Ireland. We gotta blend in. Riverdance.
Heroes.
Don't need these guys.
Become legends.
Penguins are our flesh and feathers. If anyone's gonna save us, it's us.
From the creators of Madagascar.
He hacked into our system. Dave.
Where's the sound?
Dave, your microphone, it's not on. Click on the button with the picture of the microphone.
Every time a billing calls in, this happens.
Hello?
Well,
Now we can
so
hear
annoying.
you, but we cannot see you.
Every time.
That's like talking to my parents. DreamWorks, Penguins of Madagascar.
We need to find intel on Dave's location. Hey, you! Where's Dave? Give us the goods.
So that's a baby squid.
Sorry, laddie.
I hope you like that. Thank you very much. So we have a lot of stuff to get through. So I'll be really quick. So as I mentioned, we are DreamWorks technical directors. We work on animation pipeline. Am I audible at the back? No. How about now? Okay, this is exactly like the trailer. So yeah, we work on animation pipeline. We enable artists to perform these amazing imagery and movie. We come up with workflows for them to make movies, and also we build services to help make movies. So we're going to focus on the third thing today. That's actually what we call as a transfer pipeline. Now, so why was this required? Well, we do a ton of collaboration. Movie making is not a single person job. We have a big crew working on it. So we had to have an efficient system. Why is this required? We'll come to that. But just know that movie making is a highly collaborative process. We have two kinds of data that DreamWorks produces. One is the handcrafted data that artists produce, and the other one is a generated data that procedurally we generate. Now, quick turnaround. Well, yeah, quick turnaround is required because we can't do even a single day while making movies because we have to be on schedule because otherwise the movie never gets released on November 25th. So, and also there's a ton of data going around. There's a huge amount of volume. And this was the very first time something like this was attempted outside of Hollywood. So again, the onus was on us technical directors at Bangalore to come up with a solution that worked across the board on a Hollywood animation movie. So we evaluated a couple of things. We looked at rsync and SCP because, you know, at the end of the day, this is just local and remote site. You know, like, can we use rsync and SCP? We quickly realized that, you know, we needed a little more reliability. Yeah, we quickly between Hollywood and Bangalore. We also looked at some firewall level syncs. We use NetApp solutions, so SnapMirror, SnapCache that enables firewall level, you know, replication between sites. This was a complete black box for us, and it was kind of hard, again, for certain reasons. We also evaluated cloud, and unfortunately, DreamWorks does not like to put its IP on someone else's servers, so this was out of our, we couldn't use that. So we came up with a solution, the 1.0, which was built at 2009 when the studio was established in Bangalore here. It was cron-based, as with any, you know, hacky solution would be. We used ticketing system, Jira as the backend. It was a very, very novel idea. It was super unreliable. It was not scalable. We did a couple of TV shots with it, but we quickly realized that we can't do this for movies. And Python was chosen because we wanted quick turnaround. Again, the movie production had to start at a certain point, and we didn't have the expertise nor the time to actually implement a most efficient system. We just had to get something up and running really, really fast. So, and well, once we realized that it was not going to work, we started working on version 2.0, which is actually what we're going to talk about today. We started work at 2009. It's handling hundreds of GBs of data every day between Hollywood and Bangalore. We built accountability into the system so that we can actually ask, hey, is this particular thing in US or India? Is this actually here? Can the person start working? All those kind of questions. It had to be super, super reliable because we are going to give the solution we're going to put this on production, and artists and production producers and directors are actually going to use this, and they're not technical at all. So something that would work all the time. So transfer pipeline today, it has some 100,000 lines of code. Again, lines of code is not a good metric, but it's there. It handles 1 to 2 TB of data sometimes when there's a lot of traffic. We use Python 2.7 in the studio. Again, really quick, the service is actually interfaced by automated hooks. So we have a ton of automated stuff that's happening: movie generation, particle simulations, other hair simulations or animated data. All those things are via automatic hooks that talks to the system. We also have artists directly interacting with the system. So we also wanted a system that allowed people to talk. So think REST, JSON APIs, all those kind of fun stuff. And also there needed to be a front end. We use Qt. PyQt actually to provide some nice little GUIs for people to use inside their application or even outside just on the command line. So we provided all those. This is just I don't know if it's visible at the back. This is last 2 weeks of data that we transferred one day. Sometimes it went up to 100 GB. This is bold every 15 minutes, I believe. And there's also another graph that shows we do see variation. Actually, it's very interesting. You can actually see when it's night, there isn't a lot of traffic, or towards the evening. So some interesting patterns there. So really quick, the system architecture looks like this. We're going to jump into this a little more deep, and Utkarsh is going to help us do that. We have Bangalore on one side. We have Hollywood. That's Los Angeles, and we also have a studio in San Francisco. So we needed to have a system that worked across the board. So we have a load balancer that represents the circle roughly, and we also have services, twisted services, sitting on it, reading the same file system, NFS mounted file system that enabled this. We use Redis, and we also have reliability. We also use Oracle as a backend at this point, and that something happens, and Utkarsh is going to help us, walk us through that. Over to you.
Can you guys hear me? Yes? Okay. So we'll head straight into what the technical bits of this entire system are. How many of you guys attended the async talk today morning? It was pretty good. I guess those guys covered mostly Tornado. We'll be looking at, our system is based on Twisted, so we'll be looking at how the daemons, the load balancers, the databases, and the watchdogs are implemented with Twisted. So what is Twisted? Twisted is an evented, asynchronous, non-blocking web framework. With this you can create pretty much anything. You can create a website, you can create an FTP server, you can create something like Dropbox. Pretty much anything network related is possible, and Twisted is the grandmother of all async frameworks out there right now. There are a few new ones coming out, but this was the first one, and the first one to prove that, okay, this is a reliable pattern to follow. We used XML RPC for the communication between daemons. We'll see a bit of examples of that. We have daemons, we have load balancers, watchdogs, and one of the key things is not everything can be made asynchronous. We'll see some examples of that. That's where Twisted gives up and says, okay, no, I cannot do this, you have to use a thread, and we'll see some concrete examples on when that happens. So here's an overview of what one particular code path looks like. So we have a user, a happy user. He says, can you guys see that at the back? What that's written? No? No, okay. So I'll read it out for you guys. What it says is request transfer. So the user said, okay, I want to transfer so-and-so files, so-and-so 1,000 files. What happens is that goes onto a queue. So we have a system which says, okay, at a time only about 20 transfers can happen. So it goes onto a queue. It stays there for a while. It might be 1 minute, 2 minutes, 5 minutes, depending on the load of the system. Once it gets a slot, it runs rsync, SCP, something like that, and actually transfers the file. Once the transfer is done, we no longer need the files here in India. So we archive them, move them to a tape storage or something like that. That again takes us some time. And we ping the other side over the internet that, okay, please start unpacking these particular files. So again, that goes into a queue. We have a limitation of 20 files, 20 transfers being unpacked at a time. And then you run tar_exif. That's the actual command that extracts everything. And again, you archive the tar file and you do some cleanup, and you have a happy user. He has his files. So that's the main architecture. So what we'll be looking at is just the left side of the screen. How does that work? We'll be looking at some of the technical details of that queuing, how the events are happening, and things like that. So the reactor pattern. So we're looking at just the left side of this particular screen right now. So the user said transfer file XYZ. So what does this mean? What are the things that need to be done right now? There are 3 steps. You need to create a tar file. The user said, I want to transfer 1,000 files. Make one single tar file out of it. Rsync this tar file, and then ping the other side, okay, please start unpacking this particular thing. So as you can see, this kind of fits perfectly the evented model. Once tar_cf finishes, you start rsync. Once rsync finishes, you do step 3. So that's how the evented model of Twisted helps us. And you'll notice this is mostly IO bound. You're creating files, you're syncing them, and you're pinging them across the network. So that fits perfectly with the Twisted model, async IO. Everything is IO, so Twisted was the perfect thing for this particular case. So here's what a bit of Twisted code looks like. So the user said, I want to transfer files. He gives a file list of, let's say, 1,000 files. We build a command. It's pretty straightforward. And then we use the utils module and say, get process value. What that does is it executes the tar command in the background, waits for it until it finishes, and once it finishes, it will run this particular function called self._sync file, which I think is on the next slide. Yeah. So what's happening here is utils or get process value is returning a deferred object. A deferred object was is similar to the future. If you attended the async talk today morning, what a deferred object does is it's a promise that in the future it will have a value. It doesn't have a value right now, but it will in the future. So what getProcessValue does is it returns the exit code for tar. So if it's a 0, then everything's fine, nothing wrong happened. If something bad did happen, it will return an exit code, say 33 or 45. In that case, we can handle, okay, it went out of memory, or the files were unreadable. So we can handle those kinds of cases with Twisted. And once this finishes, you do sync file. You're essentially just checking if the process value is not equal to 0, then raise an exception, highly simplified version. Otherwise, run the rsync command, and we do the same thing again, get process value, and ping the other side to unpack everything. Does that make sense? If you guys have questions, please let me know. Okay. So once you start working with Twisted, you'll figure out not everything can be made asynchronous. So one of the examples, since we are a file system kind of a service, we figured out these are two things that cannot be made asynchronous. We are listing directories with lakhs of files. That is bound to take time. But unfortunately, there is no method in Twisted which allows you to do that. Similarly, fetching the end time of files, that's just not possible. You want to find out when was everything in this directory modified. It's going to take a while. Why is that the case? Because it's asynchronous I/O. Everything that's based on file descriptors can be made asynchronous. Unfortunately, these two things are not based on file descriptors. So the common saying that everything in Unix is a file is kind of usually true, but these particular cases it fails. So for these cases, you need to fall back to threads, and Twisted gives you a really cool interface to do threading. What happens in Twisted is there's a thread pool of, I think the default is some 10 threads. You can change that, and all you need to do is run threads.defer to thread, and what it'll do is pick one thread from the thread pool and start running do list dir in that particular thread. Once that task finishes, it will call the callback on T as mentioned. If there's an airbag, you do add airbag. There are also a few interesting functions. There's a call from thread, call in thread, that let you communicate between different threads as well. So I found those to be really useful. So until now, everything was just Twisted. So I was assuming you're starting to make a new service. That's when you'll use all of this code. But as you get used to this particular paradigm of coding, you'll figure out, okay, every single problem I have is asynchronous, and maybe I can use Twisted for it. And that's when you realize, okay, I have this script, it does a certain things, and then goes to the internet, fetches some pages, maybe it's crappy or something like that, and then it figures out some more algorithms on those pages. So you'll figure out, okay, I was doing fetch page 1, fetch page 2, fetch page 3, fetch page 4. Instead of that, I can do fetch page 1, 2, 3, 4, and then as and when the pages come, I'll process them. So Twisted lets you do that really easily. It plugs in to your existing systems pretty easily. But there are a few rules you should abide by. The first one is really handle every error, put airbags. It might not sound really big, but if you have a synchronous script and you're just trying to put a reactor in between, you'll figure out if you don't handle an error, your script might never exit because the reactor is just an infinite loop. So yeah, just make sure you handle every single error that might happen. For example, if you're connecting to the Google auth API and for some reason the connection drops, you need to figure out, okay, the connection dropped, I need to stop the reactor, or I need to start the reactor again now. And that brings us to the second point. Make sure you stop the reactor properly, because it can be tricky to stop the reactor properly. So in the previous slide, we created a thread here. So if you're creating threads, there's one main thread and some additional bunch of threads running. So you need to make sure all those additional threads also exit. If you don't do that, you'll figure out that, okay, your script ran fine, nothing bad happened, but after a couple of hours, couple of days, depending on how much traffic you're getting, you'll figure out your processes aren't exiting. And why is that? Because your threads did not exit on time. So just make sure you kill all, somehow, not kill, but make sure all the threads exit properly, and then stop the reactor. Oh, and if you have a cute GUI, just put this module into your code, and the Qt event loop and the reactor will start working together perfectly in perfect synergy. And I actually found that using thread.call from thread and call in thread are a better and more flexible way than signals and slots in Qt. So you might want to try out this particular module. Any questions till now? Okay. Can you guys see this at the back? Okay. So that is how you run a twisted application. You define an application consists of different services. One might be an HTTP service, one might be FTP. So you say that's your main application file, that's where the log goes, and that's where the PID file is. But as your traffic increases, you'll figure out, okay, there are some limitations. You'll start seeing file descriptors running out. And that is because just running that command creates a reactor that uses the select system call. So what you need is an epoll system call. And it's as simple as doing that. And now you can literally scale to 10,000 connections if your machine allows, and it'll be perfect. It'll just work out of the box. So these are the main system calls used by a lot of the async frameworks. Select, poll, epoll, KQ. Select is the original one. It's found everywhere. It runs on every single device. It runs on a mobile phone. It runs on embedded devices. Similarly, there's poll. So select has this limitation of 1024 file descriptors. So you cannot have more than those many connections. Poll doesn't have this particular limitation. epoll is a slightly more optimized version of this, and KQ is the best one, but unfortunately it's not available on Linux. It's I think not just file descriptors, it's everything. Signals, semaphores, processes, everything can be multiplexed by KQ. So if you're using Twisted, you'll figure out that as your traffic increases, the number of errors that happen just because it's on a network increases quite a bit. Interestingly, the one at the top is Twisted, and being at the top is not something that's good. It's the number of errors happening. So what you need to be ready for is timing out these particular connections. So what's going to happen is your client will think, okay, fine, I've connected to my service, but I have not received any responses yet, and it'll keep waiting, and it'll keep waiting, nothing will happen. So you need to time out that particular function, and I found that this particular snippet does the job every single time. You might try timeouts provided by the library itself, but that sometimes hasn't worked. So that's a system level thing, and that always works. So you might want to include that if you're making a highly scalable system. So load balancing, we are using this particular project called TX Load Balancer. There have been no updates to this project since I think 2008. But we've been maintaining this in-house. We've added quite a bit of things, consistent hashing. We've added a lot of different ports to this. So yeah, we're maintaining this in-house, and it works pretty good. So how do we contact these services. So we've made services with Twisted until now. I mentioned we used XML RPC, and the reason we use XML RPC was because contacting the services is super simple now. So this is some code from a client, for example. What we're doing is we're connecting to example.com and saying just transfer files, which is the same function we looked at a while back. So it looks like you're just running a method on the other side, and you don't have to do some funky URL or something like that. And yeah, the main thing is it's super simple, and you can add new things to it really simply. We're also using the Oracle database and SQL. Interestingly, Twisted comes with a module that plugs right into Oracle, and all we need to do is just run the query, and it will pick a connection from a connection pool and do stuff. So we have like 3-4 connections open to the database all the time, and you can just run query whenever you want to. So how we've been developing and deploying, I'll just quickly run through this. We have Git, we build with sconce, and we have rolling deploys. We have a bunch of transfer machines. We test it out on 1, test it out on 2, test it out on 3, and the cycle continues. So message queues. So this is something interesting we did pretty recently. We started using Redis for queues. So remember the queues I told you about, the transfer queue, the unpack queue. So that's implemented with Redis. So the client goes and says, I want to unpack a ticket XYZ. So what does the server do? It simply adds it to one particular key, which is, again, that's quite technical, but yeah, it adds it to a set, and the set doesn't have duplicates, so that's pretty nice for us. And we have a looping call on the servers. What a looping call is, it just runs one particular function every 10 seconds. So in this particular case, it will run scan queues every 10 seconds. And what does scan queue do? It does redis.spop. If it returns none, we do nothing. If it does something, then we add it to the processing queue and then do the unpack business. So that's the part where we use Redis for queues. One more place we use Redis is for analytics. So we wrote this module in Python, which generates analytics in 15-minute chunks. So you'll see that the key, are you guys familiar with Redis? No? Okay, so let me back up a little bit. So Redis is an in-memory database. You say, you can say one value equals a certain value. So tp2.daemon gld queue unpack is equal to that particular list. So that's all Redis is. You store key value pairs. So that fits perfectly for analytics. So what we are saying here is tp2.daemon.ttp.events.whatever, and then a timestamp is equal to some number. So that timestamp is actually the Unix timestamp, and we do this for every 15 minutes. Interestingly, we have about 20,000 keys being generated every day, and we found that it's blazingly fast, Redis. In fact, it's so fast that people often recommend that you should not have callbacks in Twisted, because if you add callbacks, that's adding more latency to your code than just running it in synchronously. So that was analytics. Some of the lessons we learned with this project: simplicity. So again, let's go back a little bit. Jeffrey had mentioned that this service is going to be used by people who are not technical at all. They are artists, they are directors, they are producers. So it needs to be dead simple. This is something that a lot of the big companies just say it for the namesake. For example, some companies actually do it. For example, Dropbox, dead simple file sharing. Similarly, we had to make it dead simple and trustworthy at the same time. So doing that takes effort, a lot of effort, and it mostly boils down to talking to your customer and asking them, okay, is this working for you? What can I do better for you guys? The next one is testing. So before this particular project, I was a fan of unit testing. After this, I changed my mind. The reason is unit testing just makes your code look really ugly, and you're doing it for what? For testing if your function X works. Is that relevant? I really don't think so. Unless you're working in a team that's 100 developers and you have 100 people committing code on the same time, I think unit testing is not really useful. Instead, what you should go for is functional testing. Are files being transferred? What happens if I unpack a file? Those are the kind of questions pretty much everyone, me the developer, the artist, want to figure out. They want to know, is the system working or not? That's what they want to know. They don't want to know, okay, yeah, fine, your 1,556 tests are working fine. And this is the biggest one, expect failure, especially on the network. So there can be, since we are a file mover kind of a thing, there are a lot of things that can go wrong. The disk could be disconnected. The disk could go out of space. The network might be disconnected. The machine might go down. And this is happening across dozens of machines. So expect failure at every single point in your code. Go out of the way and figure out, okay, this might go wrong, this might go wrong. And once you think you've figured out everything, go show it to your colleagues, and they'll do it and do something that you wouldn't have thought of. So yeah, that's about it. Thank you. Any questions? Yeah.
By the way, the slides should be up there in case you want to browse right now.
I can see that you are using XML RPC for the calls. It will be a lot more simpler if you are using REST-based, right?
Sorry, what?
SOAP might be a little heavyweight here, but you could be using REST-based calls, right? It will be a lot simpler, right?
True, but we kind of went with what Twisted gave us initially, which was XML RPC. I think that, again, there's a ton of stuff that has happened. The development started in 2009. We were using XML RPC, but you're right. If I were to start a project today, I wouldn't do XML. I would much rather go for JSON, REST-based, communication. But what we have today is an XML architecture, though. But yeah, you're right. If I were to make a call right now, I would probably go with REST-based system. Yes. Any questions? Even if it's related to movies, it's all right. Yes, right there.
Okay, you just mentioned about the reactor event.
Uh-huh.
Now, I know there's another model like a proactor event. Is there any difference between those two models?
What is the other one?
Proactor event.
Proactor event. No, we're not. The question was, the gentleman knows about proactor event. How is that different from reactor? We are not aware of.
Not familiar with that.
Yeah, we're not aware of proactor event. Sorry. Oh, the question is which other areas do we use Python? So I should actually mention this, but DreamWorks is very, very heavy on Python. All our pipelines made in Python. So yeah, I mean, a movie animation pipeline where actually data moves between departments. The glue is Python. And now why Python? I mean, it's easy to find talent. It's easy to get used to it. If you know C or Java, it's actually it's as easy as getting, you just have to learn the syntax, and it's runnable pseudocode, right? So we use Python extensively. Of course, our high-performance systems are written in much more low-level, well, not low-level, much more performant languages like C++ or Java. But most of a pipeline, if not all, is actually in Python. And this actually is one piece in the pipeline. When I say one piece, what are the different things that enable us to make movie? Transfer pipeline is one of them. We have a lot of other things and all of them are actually in Python. Yeah, right here. Yeah. So the question is, we use scons. You want to take?
We use scons for pretty much everything. Right now, even for, if I'm not wrong, even for our performance code, we use scons for everything. It's just that we find it a lot easier to specify build rules in scons, and yeah, it runs just pretty amazingly. That's what I think.
So yeah, we used to use makefiles, and we made a big switch over to scons, I think maybe a couple of years back, and almost all our tools are using scons at the back end to build. Yeah. Any other questions? Did I see a hand there? No. Is there a question there? Shout it out if you have a question.
I have heard that compressing movie files is not so effective as compressing text files or something. So how do you achieve, what do you achieve by compressing with tar?
Okay. So the question is, compressing movie files probably isn't that efficient as compressing text files. So when we say movie files, remember those are actually the data that makes up the final movie. So remember, there's a ton of different types of files available. We found that some of them are highly compressible, some of them are not. To give you a little more detail, the tar command that you saw was our way of isolating files. These files continuously change. So we had to isolate it somewhere, and tar is quick. We don't really care about the compression that much at that point. We just wanted it to be isolated. Did you have something?
And tar doesn't have, we don't compress files by default. A lot of the data we do move is pictures, images, that's already compressed, movies, that's already compressed. We move a few text files, that's not compressed and can take advantage of this. So we have options which let you do bzip compression. By default, we do just tar, and tar is nothing but just concat all the files and just transfers it over. If you want, we can convert it to bzip too and transfer the compressed file over as well.
Minimum bandwidth. I'm not sure whether I'm at liberty to say all that, but we do have dedicated lines running from Bangalore to Los Angeles and San Francisco.
So computation is cheap, but like the bandwidths are expensive, right? So if you're saying 100 GB of data you are doing, the transfer, the upload and download each day or every year, whatever, right? It's very expensive. So using like LC 476, you can do it like much better, like even better than the bzip, right? So this could be.
Sure. Oh, but then at that point we are spending more time compressing the file.
Computation is cheaper compared to the bandwidth. Right?
That is true. That is true. But unfortunately we haven't run into that kind of a situation.
So yeah, I mean the solution that I'm not at liberty to say some of these things, but think of it as there was an existing paradigm in which we're trying to solve the problem, and at that point bandwidth was cheaper for us than asking for more machines.
Okay, so I guess we would.
Yeah, there are no other questions. Oh yeah, there is one. If there's time.
Okay, so I've got space time with a question. His Twitter handle is space time.
29.
You mentioned you were working on a module for the load balancer, which you're developing. Is there some reason that you're doing it in-house and not releasing it to the community?
I expected that question, yes. So we are in talks to get that open source. As a matter of fact, DreamWorks does contribute back to community. We open source something called as OpenVDB a while back. We had to talk about that in SIGGRAPH. So we are committed to the community. We do open source. We are in talks to get that open source. There's no reason why it has to be inside.
And we've recently started committing to something called Res. That's on the GitHub page for DreamWorks as well, so you could check that out as well.
Yeah.
Okay, so I think we should just end it up here.
Thank you very much.
So just give them a huge round. So thank you, Jeffrey. Thank you, Utkarsh. So we got a 30-minute break. Okay, so you guys can just freshen up a bit and be here in the hall exactly at 4 p.m. Thank you.
Speak something.
Blah, blah, blah.
Hello everyone. So there's this open session going on Audi 3 and it's being organized by Z Omega. So those of you who are interested in attending that talk and attend that too, it's in Audi 3. Plus there are a couple of more parallel sessions being held in Audi 2 and on the first floor, I guess. So you can just check out the board outside and attend your favorite one in case you want to attend. Thank you. So we are starting with this next talk, which is GPU Accelerated High Performance Computing Primer. The talk will be given by Ashwin Ashok and G. Raja Suman. So both are here. Can we have a round of applause for them? I'm particularly interested in this talk because I think it got the highest number of votes when it was on funnel at PyCon. So Ashwin Ashok is a student at Vignan and he's interested in open source and embedded systems, whereas G. Raja Suman, he works at TCS and is fond of embedded C and Python. So just enjoy the talk.
Hello? Okay. So I'm audible to everybody, right? Okay, so before I start anything, I'll make one thing clear. If anybody has done CUDA programming or OpenCL programming before, please raise your hands up. You can sleep. Okay, because there's nothing new I'm bringing to the plate here, but what I'm trying to do, what we are trying to do is try to bring awareness, because everybody is like, if I want to process something, I'll put it in that power. That system is really powerful. I'll just shift it there. No. If you buy an NVIDIA GPU or if you buy a AMD GPU, you can do lots of stuff faster than servers can do stuff. So you have lots of power in your hand, and I want to make sure that everybody knows. I won't bore you with my APIs. I won't bore you with my functions. I won't bore you with anything. All I want to say right now is, if you want to do stuff faster and if your algorithms are parallel or can be made parallel, you'll have amazing speed up. So, and the other thing I just want to say is,
most of the stuff which I wanted to cover was already covered in Medusa. Like most of you guys were there in Medusa talk, right? Okay, so it was a nice, super talk. So most of the stuff was covered there, and I hope some of you have observed, like whenever he went like this, Python 2, I'm sorry, can you see? It says, for my system it says GCC, but for the Medusa talk guy it says LLVM. Okay, that will make all the difference in this talk. Okay, have anybody observed that? Okay, that will make all the difference. So GPU accelerated HPC problem. I just made this up, okay? Yes. I just wanted to pull some crowd out, so I just made this up. So the end of an era. So by the time Pentium chips were coming into the market, it didn't make any difference. Like 5 years ago, I had a 2 GHz processor. I still have a 2 GHz laptop. That didn't change. But the only transistor count increased. But this has nothing to do with performance. I'm just plotting a graph between clock speed and transistor count. So basically what I'm saying is, even though manufacturers are putting more transistors into CPUs, the performance gains are only like marginal, like 1%, 2%. So if you want to do anything, like if you want to increase the performance of your processors, you need to do some tweaks like transistor level tweaks. I won't bore you. I'm an electronics guy. I won't bore you. So when you do that, when you increase clock frequencies, your power dissipation goes up. So with great power comes great responsibility. With great clock speed comes great power consumption. Remember that. So let's go too fast, too parallel. So what is parallel? Everybody knows parallel. So I don't have to explain. If you know multithreading, you know parallel stuff. But this parallel is a new level of thinking. It's highly rewarding and challenging, and the hardware is already there. You don't have to buy new hardware. It's already there. If you play games, it's already there. So I shamelessly copied this from the Go programming language slides. So I'm just telling, if one guy can do a job in 10 days, 10 guys can do a job in 1 day. That's all I'm going to talk today. So race to mini-core mountain. Since the Pentium fiasco where clock speeds are not increasing, like Pentium was like, Intel was like, you know what? Let me put another guy. Let 3 guys do the job. Let 4 guys do the job. And so, AMD, whatever Intel does, they just copy. So, okay, it's the other way around. It doesn't matter. So, they just did the same thing. They just changed where the CPU cores were, and they called it a new processor, whatever. So, it's not really a new concept. This concept is not really new. I'm an electronics guy, right? So I deal with this shit every day. I'm sorry, crap every day. So back in 1970 and 1980s, when these chips first came out, people had to do floating. That's when IEEE floating point specifications came out. So these 8086 processors can't do floating point math without a floating point unit. How many of you guys have had to deal with IA32 assembly? Awesome. Oh, you are, dude, you're up. So what happened was, okay, nothing happened. So these guys used another chip called 8087 and offloaded the floating point part there. So basically, what Intel is doing is just copying what it did back in 1970 and 1980s. It's just bringing up Xeon 5 core processors, which have 61 cores. So more people gets a job in. So have a laugh. So everybody got the job? Doesn't matter. So world's first open science supercomputer it has 18,688 nodes, and each node has 16 core opterons. Now this makes sense. Since I was telling more people, less number of time, that makes sense. But why the NVIDIA? Like, you should be asking, hey dude, that K20 chip costs crap load of money. Why put that? Because that is where the magic takes place. The AMD chip does nothing. It only does memory transfers and stuff. So in most of the major supercomputers right now, the GPUs do the magic. So why use GPU? Please read the slide. Explain. So why use GPU for computing? One thing, CPUs are hitting the wall. Most of the CPUs are even if you wait for 5 years and buy a new CPU, it doesn't matter. It'll still be 2.3 gigahertz, 32 core. It won't matter. But and also development of parallel algorithms is taking place. Since the last 15 years we've seen, okay, I was a small kid back then, 15 years, so I'm just saying, we've seen a lot of parallel algorithms come up. And extremely powerful hardware that's cropping up, and it's not really a new idea. I know NVIDIA has a bad name in the open source community, but this is one thing they're doing it right. CUDA, they're doing this thing right. Why? Because simple. When you say that four cores do the job in less time, what happens when you put 240 cores? So NVIDIA is just going I'll just keep on putting cores. It's a good thing. It's a good thing. And I don't use Apple products, but I have to give this one to Apple. They're the one who started the OpenCL stuff. So what the OpenCL stuff does is really interesting. So first of all, if you want to increase your performance, for a program, if you want to increase the performance, there are 4 ways. First is you can put multiple CPUs, or you can use OpenMP, #pragma OMP before a for loop, and boom. And you can use GPUs, or 7 years ago when CUDA was not there, people used to fool OpenGL into thinking it was doing math. So that's really complicated stuff. So what Apple did was, it made a common C99 programming language for all these. That's OpenCL. Next. So I know you guys are talking, hey, this is PyCon, this guy's not talking about Python. This fine, it'll come. So where's the embedded here? We're in the embedded segment, right? I'm an electronics guy. I want stuff to get smaller, not bigger. So we are not doing anything with Intel now. We replaced Intel with ARM. The CPU is only doing the memory transfers, right? It's just doing mallocs and control stuff. Why do you need Intel to do that? ARM can do that. And I didn't put, NVIDIA guys are doing it, I'm just saying. So NVIDIA guys put a powerful GPU and coupled it with the ARM. And that thing, it's called the Jetson toolkit. It can beat my laptop with Intel. So it has 300 cores or something. I'm just saying, those kind of chips are coming to the market right now. Tegra chips are hitting the market. So those are insanely fast. Am I supposed to do after this, right? Okay. So AMD is bringing 5 GHz, 6 GHz stuff. I already told you, with great clock frequency comes great power consumption. If you want to pay the bills, you pay. So CPU architecture is more about how fast can I do a single task. Latency. CPU is all about, remember, CPU is all about latency. How fast can I do a single work? But GPU is more like, how many tasks can I do? Everybody getting the difference? CPU 5 gigahertz, how fast can I do a single task? GPU is like, how many? Throughput. That's why they don't have 16 cores, they have like hundreds of cores on SMD cores. Now this guy will take over. Hello.
Yes. So let's see what we intend to do with our GPU. Basically, we have our application code, which which we may consider as consisting of some sequential code, something like if the data is dependent upon a previous input or something such kind of sequential stuff. Let the CPU handle it. I'm not going to touch this kind of these kind of things and let the CPU itself handle it. But I have some kind of code, something like computationally intensive functions. What this program intends to do is switch these contexts into a GPU and thus increase the throughput. And now, why do we need to use Python for GPU? Well, it's simple. We do know about the Zen of Python. It always tells us keep it simple, keep it simple. So what GPUs are, they are everything that scripting languages are not. They are highly parallel, and thus what we intend to do is shift all the work which are highly parallel to a GPU and leave the rest of the things with the CPU itself. Thus you could see that CPUs are largely restricted to control, and as Ashwin said, CPU always depends on how many tasks I perform per second, whereas GPU deals with how much amount of tasks do I perform. So if you integrate Python and CUDA in order to do this kind of stuff, we can do it with PyCUDA, as well as we have something called as OpenCL. And let's see what PyCUDA is. Okay. See, PyCUDA was is a baby of Andreas Kolasker. He mainly developed this thing because he was a great programmer. He was probably interested in this, and he wanted to do and achieve his stuff much more simpler. So you could see that we have a kernel function which we need to implement on the GPU, and this kernel is CUDA-C, but sometimes it is not. We could totally perform the kernel function into a Python, but sometimes we need to make a compromise, and let's see why we need to make that. You see, this is the basic flow of the CPU stuff on Python. Like, you edit it, you compile it, you link it, and then you run it. That's for the CPU stuff. But for the GPU stuff, you need to specify the code which you need to specify some stuff that this part belongs to the GPU and this part belongs to the CPU. And so here we just move on to something else. Over here we have something called as a source module, and this uses an LLVM and PTX. It has a PTX, and then we have our stuff to be implemented on a GPU. But you see the box over here, that whole box is of the PyCUDA, and we needn't literally do anything. PyCUDA takes care of all our stuff over here. So again, so Python, it follows the Zen of Python, makes our task simple rather than following the blatant C code, which you need to, if you follow the C code, you need to follow all these things. So Python. Here. Yeah, you could read that. That's a pun kept by my brother. So let's just go about the setup and demonstration of PyCUDA. How a lot of queries have been pouring in on how to set up this stuff and how to use PyCUDA. So setting up the environment requires you, suppose you are using a laptop with NVIDIA GPU, you need to install its drivers first in the first place, and then you need to import some basic stuff before starting your code. You need to import the PyCUDA driver, some tools, and the auto init. And then we have the heart of our GPU programming. It is called the kernel, and in order to write the kernel, this kernel is essentially to say that this part of the program belongs to the GPU and it must be executed by the GPU. Thus, we use the prefix __ global __. This tells us that this is a C function, and this prefix tells the compiler to generate the GPU code and not the CPU code while compiling it. And inside this kernel function, what we have is our code, and it also has a return type and the function name along with a few arguments. Let's see how this thing will look like. What do we mainly intend to do with the threads is that we have some computationally intensive stuff, like suppose we have a for loop and we need to do some iterative operation like 128 times. What my kernel does is, instead of performing the 128 operations on a single processor, I made multiple threads and I perform the 128 operations on the whole 128 threads of the GPU, and thereby reducing reducing the time taken in order to implement this stuff. But this is a Python conference, but please bear with us. You need to know some of these stuff before starting or diving into PyCUDA. We have the concept of blocks as well as threads and grids. Like you could see that the block is essentially a group of threads and a grid is a group of blocks. This concept will be very useful for performing stuff like image processing and such kind of stuff like 2D processing, 3D processing. And so here is a basic example of how our kernel would look like. You see that here, consider the example of having a for loop and having to perform a multiplication operation using that for loop. So what we are here doing is, we are using a thread. This is a structure, and we are taking that 128 loops and giving it individually to one single thread, and thereby we are reducing the number of steps taken. Yep. Well, you could see that this is how a simple kernel function would look like, and let's go move on to some bigger examples on image processing as well as signal processing. Ashwin, will you like?
Hello? Hello? Can you hear me? Okay. So, actually, sorry, Anya. I asked him to drop certain slides because you guys are already bored. You've seen too much code already. Is it not? Let's be frank. So, I thought, why not show you some demonstrations? And again, I don't want to show you big things. I just want to show you small things and show that you can do it. I don't want to show you big things. You can write this. You can do this. Okay. So, okay. Everybody can see my code, right? Okay. View presentation, right? Okay. It's bigger, right? So what this program does this thing is the simplest PyCon program ever. So what this thing does is simply takes two arrays and multiplies them element wise. Just takes two arrays and multiplies them element wise. That's all it does. Okay. And I'm taking exactly 2 power 16. Is it 2 power 16? Yeah, 2 power 16 elements. So I'm taking two arrays of 2 power 16 elements and multiplying them each. And then I'm benchmarking. Like, it's not even benchmarking. I'm just saying CPU, how much time is taken for the CPU and how much time is taken for the GPU. Let's see. So,
geez, that's a goof up.
Okay, it's not a goof up. It's not a goof up. My laptop fell. So you can see CPU time was like 7. This is floating, right? So it's 0.0007 something. And the GPU time was like 0.11. And I'm here promising you that GPU is fast, GPU is fast. What actually happened in the background was, you see, the GPU code has to be compiled. GPU code has to be compiled, and this compilation takes place, like one of them wanted to know how this compilation takes place. NVIDIA is not telling us, but what I know is there's a language called PTX. Just like there's a language called just like this assembly for Intel, there is PTX for the GPU. So they use the LLVM architecture to kind of compile this C99 code into the PTX. That's what happens in the background. That is what's slowing this thing down. So if I take 2 power 32 elements, this delay won't matter, because that time CPU will be lagging far behind. We'll see that. So let me take this program with add.py. It's basically the same code as before. All I'm doing is, even if you can't see it, doesn't matter. All I'm doing is I'm repeating the experiment. I'm repeating the experiment over and over again. And each time I'm repeating the experiment, I'm increasing the number of elements by a factor of 2. Got me? I'm repeating the experiment 28 times, and every time I do that experiment, I'm increasing the number of elements in the array by a factor of 2. Okay? So I run it. Okay. So awesome. The CPU thing was slowing it down. What happened here was, and can you zoom? I'll zoom out. What happened here was, can you guys see the difference? See, like when I had 2 power 1 element, when I had 2 power 2 elements, when I had 2 power 3 elements, and 2 power 4 elements, and so on, the GPU was actually slower. Anybody got me? The GPU was slower. Why? And you see the delay is consistent, because, and that delay is the time taken to compile the PTX code. But once I hit a number like 2 power 20, 2 power 21. So you decide which is faster. So basically, if your CUDA programs are slow, it is because you are either not keeping the GPU busy enough, or you are giving a very small number. It takes an array of 2 power 64 size to actually kick the GPU out of slumber. Okay. So, and this is how the graph. This is a graph between GPU time versus CPU time. So as you can see, as my element size increases, it's actually performing faster. And this, I think this is exponential scale. Okay. And let me show you another program. What should I show? Julia. Anybody into fractals? Anybody? Ladies here, chudidar patterns stuff. So fractals are self-repeating stuff, okay? You take a triangle, and on each side of a triangle you put another triangle, on each side of that thing you put another triangle, and you keep on doing it, you get a fractal, okay? And fractal antennas are electronics. So, if you want to do a fractal on a pure Python implementation, it's real slow. It's as slow as finding the Fibonacci number of 340. It's that slow. But GPU is real fast. Yeah. And this fractal has a dimension of 2560 by 2560. It's that fast. I dare you to do this on pure Python or even PyPy. You can't get this speed. I dare you. So, and I told you, I promised you self-repeating stuff, right? So, I zoom this part, same thing. Zoom this part, same thing. So, and I promised you stuff in like signal processing and image processing. So, this is another example I have. So actually, I have a color image on my hard drive. It does RGB to gray. It's a very simple algorithm, but it's fast. It's just fast. I mean, you can't you won't know it's fast. You won't notice it's fast, but the file size is really huge. The file size is really huge. So, and again, this is. Can you observe the difference? Can you observe the difference? The other one is blurred, right? So this is a simple image processing application in PyCUDA, where you just blur the image. Now, it's just a filter. So filter applied on stuff. So I actually wanted to do something so much more, but you guys are bored and tired. But I don't want to tire you any longer. But there's a lot of stuff you can do in PyCUDA, many times faster than Spark, faster than Medusa, faster than any other thing can run. Only thing is you have to learn how to use PyCUDA and writing this thing is a pain in the. So what we do, what Andreas Klockner is trying to do is try to create a Pythonic wrapper. But I'll tell you what's the problem with wrappers. And the problem with being lazy is Monte Carlo. Anybody heard of Monte Carlo methods? You heard of Monte Carlo methods. Fine. Awesome. So what we do in Monte Carlo methods is we simply keep doing the experiment again and again and again and again until we arrive at a result. We just keep doing it again and again. So in this example, I am calculating the value of pi. It'll take some time. Tea break, anybody? So I deliberately put this last. Okay. So there is something you should observe here. GPU took 19 seconds. GPU took 19 seconds and CPU took like 0.06 seconds. Why? Why did GPU fail here? Why did GPU fail? It failed because I was using wrappers. You see this stuff? I didn't write C code like before, right? I didn't write C code like before. I used something that calls another C code. When that happens, lot of memory transfers takes place. When you have lot of memory transfer, it will only slow the program down. So if you want to test if your thing works on GPU, you can use wrapper. But if you want more speed and stuff, you need to go for pure C. Okay? Q&A session. Any doubts? Okay. So just be careful while writing kernels. Any doubts? No doubts?
Did we bore you?
I'm sure we bored you, but huh? Which one, sir? This one?
Ray tracing.
Is it doing ray tracing process?
I'm not doing ray tracing. I'm just calculating the value of pi.
Okay.
Oh, fine. You guys have time to listen to more of my crap?
Yeah.
Okay. So, so I didn't really tell you what formula I was using to calculate pi, right? I didn't tell you that. All I did was I put a circle inside a square and I started throwing stones. And then I counted how many stones were inside the circle, and then I counted the total number of stones, and the ratio happens to be pi by 4, because the ratio between area of circle and square is pi by 4, right? Simple. Happy? Okay, there is one last thing that I'm not telling you, but which I want to tell. You guys have been very patient with me, so I'm showing you this. So people are asking, do I do ray tracing, do I do stuff? What kind of stuff I do with PyCUDA? So this is the simplest 3D example I have. Okay? Everybody have it? This is the simplest 3D example I have. What I'm doing is, I'm again trying to calculate the value of pi by putting a sphere inside a cube. That's all I'm trying to do. And I'm trying to represent this process as in graphics. So, and what is the source code is small, pretty small code. I don't want to scare you with 100 lines of code. Small piece of code, and I'm heavily relying on Qt libraries. Qt does most of the GUI work and drawing stuff. And the other awesome thing is, there are not one but two GPUs in use right now. Didn't get me? Didn't get me? There are not one but two GPUs in use right now. So my laptop is an Optimus laptop. So it has Intel CPU, an Intel GPU, and an NVIDIA GPU. So whatever my NVIDIA GPU does is simply calculate. My Intel CPU, my Intel GPU draws stuff on the screen, and my CPU, it just coordinates and memory transfers. So so it takes some time to get over it, but once you understand, it's easy. So basically, this talk is all about a primer, a starting point. Anybody can do CUDA. Everybody should do CUDA if they want to faster code, if your code allows it. Okay? I'm done.
Any queries?
Any doubts?
He has a query. Yeah.
You can switch on your mic.
Okay, fine.
Yeah. It's on GitHub.
We put it on GitHub.
It's on funnel.
You could refer our funnel, and
we don't do, we see one misconception I want to clear. We don't write a lot of code. We don't put a lot of code in JIT, but we put a lot of code in hard drive. So don't expect that code.
So this is a follow-up question to the question you asked after the Spark talk. I'm over here.
Yep. Okay.
Okay.
So you were like asking him if it was possible to use GPU computing for Spark.
I was.
Yeah, but the whole idea of Spark is everything is done in memory. You just throw gigabytes of RAM at your problem. But that is not really possible with a GPU, right? Because if you're dealing with a GPU and a CPU setup in a massively parallel framework, your main bottleneck is going to be memory transfers between the CPU and GPU.
Yeah, that's what
that is at least my understanding. So how exactly do you think that something like Spark can be done using GPUs?
Like Andreas Klockner is trying to do here with my Monte Carlo stuff. I mean, this is not optimized. See, he's calling functions like this, pycuda.qmath. Can you guys see? he's trying to call functions like this. I'm trying to do something similar. Like if Spark can allow it. Like Spark had ML functions, right? Machine learning functions. Machine learning functions are like basically some of them are parallel in nature. Autoregressive methods, TVAR, MVAR methods, they are actually parallel in nature. So I was thinking, like Spark was, all the Spark person was talking about parallel stuff. So why can't some of the code might be offloaded to CUDA or OpenCL. OpenCL is much more liberal when it comes to stuff like this.
All we want to say is that just put the stuff which the CPU is good at with itself. Don't throw it at the GPU. But if you find something in your code that the GPU can do, like something parallel stuff, something really parallel stuff which you can eliminate, move it on to the GPU. That's what we want to say.
Lot of map reduce stuff can be done on GPU. That's really fast. Map reduce is really fast on GPU. Okay. Any other questions?
Yeah.
Okay.
Just a second. I was a little confused on your last line when you said 2 GPUs were being used. That is the same for all the processes where you were doing using GPU, right?
No.
Maybe. Because
it's a likely scenario, right?
Huh?
It's a likely scenario.
We'll see. See. When I say LSPCI here, it shows both Intel and NVIDIA. But when I do LSMod, the NVIDIA driver doesn't show up. But when I do LSMod, while the program is taking place, NVIDIA.
So that
I think both of them are running at the same time. See, NVIDIA doesn't talk about what happens in the background. That's the problem with them. AMD is really liberal with their code. So if you want to know what happens with AMD, you know. But what happens with NVIDIA, even I don't know. Nobody knows.
Okay, thank you.
Questions?
Oh, lot of.
Hey, don't be hard on me. I'm not a CSC guy.
Just one question. Are you running Bumblebee? You said yours an Optimus laptop, right?
Yep, Bumblebee.
So the last time I checked Bumblebee, it was a pain to get NVIDIA and CUDA to work together. So has the situation improved?
Not quite. You know, I'm using. I'll show you. What is? Okay, I'm trying to increase the screen, but can you read the font over there? I'm using Manjaro. I'm not using Ubuntu. Like if I use Ubuntu, Fedora, and all these mainstream distros, you know, the problem with the open source community, I mean, I don't have a problem. They have egos this big. They have egos this big. Like, no, this is open driver. I want an open system with open drivers. Hey, you don't know how the hardware works. How can you design a damn driver? So, leave the stuff to the professionals. You can't do drivers, don't try them. Let NVIDIA handle the dirty work. But Ubuntu is trying to do like my driver, my display server, my drive, my stuff. Doesn't work out. If you want to do PyCon on Linux, please use Arch or Manjaro or any other Slackware, stuff like that. Non-stream distros.
So
Bumblebee too.
One last question.
Yeah.
So PyCon, the examples all contain C code that is being wrapped and executed on the GPU, right?
C code is not being wrapped.
Okay.
Here.
Oh, fine. I have some problems.
Basically, in every PyCon example, there's I've only looked at the examples, by the way. So there is always a sizable amount of C code there.
There are some QA programs which are absolutely no amount of C code, but C code is running in the background. Some other function is calling it.
So it is possible to avoid writing C code and still have to make things run on the GPU with the
you want to say Python. You don't want to. You're basically trying to say that you don't want to write C code at all, right?
Yeah.
You can see NVIDIA teamed up with Continuum Analytics.
Of course, yeah.
And they're trying to bring a NumPy accelerate. I heard that's what it's called, right? NumPy accelerate. They're trying to.
Is it going to be free?
No, you need, like I took an academic license from my HOD sir in college, but It's not free. It's really costly.
Number itself doesn't have that functionality. It's only Number Pro which is not free, right?
Number is like open source. I can do sudo update.
No, Number is, but the Number Pro which has this feature, GPU acceleration built in for Number.
And even that is half, but it's because, sorry, Number Pro's implementation of GPU, you still need to have a knowledge of threads, blocks, and stuff. There was 2 years ago, my memory is fading, but 2 years ago, there was this project called Copperhead. There was a layer.
Yeah.
It really resembles STL.
Yeah.
So
still there. Yeah.
So you can do like Copperhead allowed us pure Python program just for putting a decorator, right? That is not being maintained.
Okay.
I don't know why. So
Tiaro is not being maintained or Copperhead is not being maintained?
Copperhead is not being maintained.
Okay. Thanks a lot. Yes.
Any other doubts? Wait, can you put your hands up? That guy? Okay. Which guy? Oh.
Yeah, hi. It was my understanding last time I checked that the consumer level GPUs only run single precision calculations. Is that still true?
No. See, the CUDA, I'm not so sure about OpenCL, but with CUDA, they have this compute number, right? Compute 1.0. Like, compute 3.0 supports double precision, I believe. You check. I run a real crappy old GPU, so you check. My thing is like 4 years old, so.
Okay, so we would just wrap this up. So give a round of applause for them. I guess you people are interested in that, so if you want to catch him, you can catch him afterward, because we have got a session here right now, and a pretty interesting one. So, thank you Ashwin.
Yeah.
These guys didn't have an understanding of what embedded using Python. You need to use C for embedded using Python.
Yeah, so we'll be starting with lightning talks over here. We've got an interesting collection of 8 lightning talks that are going to start in another 2 minutes. So I would request everybody to please attend this. This is going to be real fun now.
I'll just leave it here. Excuse me. Thank you. क्या बोल रहे हो? मैं बोलता हूँ तू रेडी करवा दे। कौन? इमीडिएट मत करो। बिल्कुल भैया। और कोई नहीं? और कौन? इलेक्ट्रिक टॉक लाइटनिंग टॉक वाले कौन है? पुनः कौन है? नाम किससे अनाउंस करो?
Ryan. No. Hey, Ryan, not me.
Arey, there are 2 headsets, na? Just keep it on. Turn it on.
Uncomfortable.
Just comfortable. That's the idea, man.
Okay.
That's why you are putting on your right.
I don't see the mic. Please don't turn me on.
No. Oh, yeah, you can shout whatever you want. Just don't use some of the words. So when you want to turn it on, just speak something. Okay, it's okay?
Yeah.
Put it in your pocket. Put it in your pocket. Hi. Can you want a photograph? Today? Photograph. Photo lo yaar.
Where's my headset?
I'm not giving you a headset. I need a pic with you. You're so famous, man. You're giving a talk. There you are.
John?
Wait. Come. So, now Ryan is a celebrity. Yeah. Oh. Come. You know what?
So I'll just short this up.
So we're going to start with lightning talks. There are some rules with lightning talks. Each speaker gets 5 minutes to present the flash talks. There are no Q&As to it. The first two speakers are the youngest participants for PyCon India, I guess, ever. One is 9-year-old and the other one is 12 years old. They are like awesome Python programmers. I feel ashamed at times. So yes, so we are giving them extra 5 minutes each because they've got some real cool stuff to show. So first one to come is Rayan. He's going to show us some cool tips on Arduino. So Rayan, are you ready?
Yeah. No, you can keep it here.
No,
Sure.
this will be fine.
Okay.
And you are alive. Can we have a round of applause?
Yeah, not really. Yeah. So, never really been in these people before, but anyway. I'm Rayan, 9 years old, of course. I've been doing C programming for Arduino for about a year or so. So basically Arduino is a single board computer. Well, many of you might even know that by now. So basically the chip itself is a 28-pin chip. It's called a 80 Mega 378P, I think. Pretty confusing name. Yeah? Okay, 328. So basically, to start it off, you can't really kick it off with some stupid USB stuff, hacking stuff. No, you can't do that. Here's some special things. First, you have to connect the pin 8 to 22 to pin 22. Then you have to connect pin 7 to 20. And yeah, then you have to take your 16 megahertz crystal, which I'll show you later on when we get to the board. To between pins 9 and yeah, basically there. So you have to connect the 60 megahertz crystal to between pin 9 and 10. Now if the crystal does not kick off by itself, then you'll just have to take a 22 PF capacitor, put one on pin 10 and the other on pin 9. Yeah. But one thing, don't mistakenly put your pin 1 to ground because that will just reboot the whole system. But if you want to reboot your whole system, then you can do that. I wouldn't do that if I were you. But one last thing before we get on. The pins 2 and 3 there, basically you can use them to talk to the PC as a serial port. Well, basically they also program the chip. So you can move on to the board now. These are all the components you need if you get an Arduino. I mean, I have a green one. Doesn't really matter. But you can see the power inputs in the bottom right. And then the analog inputs. There's a chip above them. Above that is a 60 megahertz crystal I was talking about. And there's a random button there. I don't know why you would want to use that. Okay, anyway, on the top over there are pins, the different digital pins. Now there's ground. There's only some grounds, and then the different other pins. This is the USB port, which is what I use to program I don't even remember what you call it, but it's a chip. Another chip that's actually connecting all the way down to the chips. This is what pins 2 and 3 use to program the chip. And then here we program. It's not that much like Python, but there are some similarities. So I'm just going to go through this. So basically you have the Arduino itself right here. I don't know if you guys at the back. You guys can see at the back? Okay. So basically the chip here. This is proprietary cable. I use proprietary. I don't know what you guys are going to use. Probably some crappy USBs. Well, I use USB though. So yeah, let me just connect this. A bit confusing sometimes, you know. sorry. So basically, I've got one end of the USB proprietary whatever connected, and then I'm just gonna untangle this. Just a minute. So yeah, Arduino on one end, computer will be on the other end. So let me just basically I have to find this port first. It's kind of annoying at points.
Wait, I'll help you.
Yeah, right there or someone? Someone? I don't think it's gonna. Yeah, bust it. It's on. The green light's on basically. We haven't programmed anything on it, so it's not gonna blink. But I don't use these lights because they're very annoying. It's not funny. Serious. It's not funny. I'm gonna use a breadboard right here. Doesn't look like a bread. It looks like a pizza to me. But anyway, LEDs, of course. That's what I've been doing for the past 1 year. That's how I've been doing Arduino. I know you guys didn't find that funny. So basically, then you have to take a resistor. I don't think capacitors will work on this. Oh, already blinking. Oh god, that's a broken resistor. I don't want to use a broken resistor.
You want me to get a resistor?
Wait, found a resistor. Sorry. Just a mess down here. So then just take this. You can do it any order. I'm just doing it in this order. So yeah. Guess the resistor has to go there. I don't remember. I'm gonna use this laptop to control them. Basically, I have to take these jumpers. Yeah, they're called jumpers. Don't mistake them for the jumpers that we wear on our legs. Okay, so first, this is what I do, and probably you guys should do too. Connect the inputs to ground, so that you got a test. So then, open a blink, please. So you go to, so if you just want a quick example, you just go to sketchbook, go to sketchbook, and then go, oh, it's not there. Okay, go to examples, basics, blink. Should show up any second. Oh, I think it's here, yeah. So this is basically it. I'm going to explain all this that's happening here. Press the tick.
This one?
Yeah. Now that's verified. Now press the arrow. The side arrow, this one.
It's compiling, just say.
Okay, after it's done. Okay, now. Now it's uploaded, kind of. Oh, now working, eh? Yeah, I guess. Okay, yeah, it's still uploading. So basically, while it's happening, what I just explained to you what's happening here. The gray outputs is they're just comments, very similar to Python. So is it? Yeah, it's still uploading. Been a long time since I've used this laptop, but yeah. Anyway, so okay, you got something wrong. Well, anyway, oh god. So basically, these are all comments, the things in fade writing. You've got the void setup. The setup is basically where, of course, as it says, a setup, where you're setting up things, getting what LEDs you want to use, I already use 13, okay, yeah, got it, I got the, yeah, because it says pin 13, right, so let's get this to 13. This 13, yeah, this is 13. Yeah, so pin 13 right here, because there's pin 13 right there, so you have to find the 13 here. Yeah. Play. So it's just compiling. So so it says pin mode, right? That's a pin, and then you're putting output means it's one of those outputs, and then you go to void. Void it is the nope. It's only a pin.
So we have uploaded the sketch.
Yeah. I was, but that's done. Something wrong here. Yeah, the LED right here. Guess I don't know why the LED is not.
Take your hand out. Take your hand out.
I don't know what's wrong with the stupid LED. My head just gone. Oh. Well, one more. You see all the setting things are ending with semicolons. That is compulsory. If you don't the whole program if you do the whole program, you just go blah. I don't understand this. That's all it's gonna do if you don't put the semicolons. And then this digital write is where it's writing this program down, and digital read, I don't really remember what it does, but just don't laugh, it's not funny. And then the void loop is actually, it's the reprogramming, the void loop. It's called a loop because it just goes on looping and looping and looping once it's done doing it once. So once, twice, once, twice, blah blah blah. And then the delay right there is, it says 1000. That means 1000 milliseconds. So 1 second basically. Now that's what my LED is doing. Oh my god, it's still going. So yeah, just don't look at the time uploading and stuff. The bottom stuff is just, I don't see it, so you shouldn't really see it. So yeah, basically, and then we go down, and it always ends with a curly bracket. See, what's funny about that? Basically, I'm going to do real stuff now. You can buy the Arduino itself for 500 to 600 rupees online. I don't know how much I got it for. But yeah.
Alright, thank you so much, Ram. That was excellent. Big round of applause, please. Alright, so this is just one of him. So we've got Shashank, who's going to talk about Pygames now. So Shashank, please, round of applause for Shashank. He's just 12 years old. Thank you so much.
What? Yeah. One. Oh god. Never had this problem before. Lol. Oh god. Yeah, sure. Just take.
HDMI converter. Right here.
Wait, I don't think this is.
You can catch him out for autographs and stuff, okay? Hello? Hello?
No, it's working, it's working. You just keep the program open. Okay. Yeah, so my name is Shashank. I'm 12. I got really interested in Python a few years ago, not too long. Yeah, so it's really a nice hobby for me, and so I found it interesting to make Python games. So all I'm working on is stuff that has to do with games and stuff like that. So what I'm going to tell you about today is something called Pygame, which has been developed by a few software engineers to make graphics using Python. Yeah, so they're not, yeah. So basically you have to, the way you install it, I would highly suggest not using Windows for this download. No, I'll just show the URL. This one? How do you? Yeah.
Open this.
Yeah. What the hell?
Don't rush.
Yeah.
Easy. Keep talking to people.
Yeah, sorry, I just not used to this system.
You'll get used to after this one.
Yeah. So the URL is, just a second, I'll just go to a new tab. Pygame.org. Now there might not be a great connection. Okay, it's here. Yeah, it might look a bit weird at first, some projects. It's kind of like a social network as well where people share their projects. So if you go to downloads, what I usually do is I get the latest version of Python and the latest version of Pygame. So usually it goes well for me. Yeah, so here's the stuff for Windows, Unix, blah blah blah. So once you've got that, once you've got that, basically it's easy to program if you have a good idea of Cartesian coordinates and all the basics. So I'm going to run the program. Yeah, so there's my program. All it does is there's this big square that goes around bouncing and it just eats all the green squares. It's a weird idea, but you'll kind of get used to it. Okay, so I'm going to go into the source code of this. So, okay, the source code. Yeah. So basically, yeah, Pygame, once it's downloaded, you have to import it. It's a module. It's separate from Python. It does not come with Python. And then I import this thing called SYS, which is used to quit the program, and random. Then, okay, this one is all about collision detection. Otherwise, how will the computer know when the squares intersect to make one of them disappear? It's like in a video game, if someone gets shot, you have to use collision detection to make sure the bullet is into the guy, so then you just kill him. Okay, this goes first. So basically I've defined do the rectangles overlap, short form. Okay, rectangle 1, rectangle 2. For A and B in this is all easy. Just check, this is all Python code to see if one is in the other. Just point inside rectangle, A left, A top, B, all the other directions. If it's true, then it returns it, otherwise it doesn't. So basically it now knows if something is intersecting or not. And then it's defining is the point inside the rectangle. So it wants to intersect even when the smallest point is inside. So then you set up pygame.init, and yeah, that's the way you start Pygame in any program, even if it's imported. So my window is 400 megapixels high and 400 megapixels wide. That's basically easy Cartesian coordinates. So I make these direction variables. This all is Pygame. You have to know this. I'll just select it to make it look easier. These four. One is the direction that is left and down, which would be what do you say? 5 o'clock, I guess. No, 7 o'clock. Yeah. So down right is 3. You have to make sure these are defined, otherwise you'll have a hard time just memorizing all these stupid numbers which are so useless. Whatever. Okay, the speed of moving, I've kept it as 4. Not too fast, not too slow. Most people will know these color combinations. So in order for me not to type, again, random numbers, I define black as blah blah blah, green is this, and white is that. So basically in the end you just need to draw the bouncer and make it move, and then make the food just randomly pop up, which is easy if you have a good knowledge of Cartesian coordinates. So that's it. That's how simple Pygame can get, and how useful it can be, as you can tell from the program. I'm also a beginner, even with Cartesian coordinates. Yeah. So this has been a great opportunity for me to give a little introduction to what I'm doing with Python, and how to let you know what I'm doing and how it has been useful for me. Thank you.
Thank you so much, Shashank. That was wonderful. Now we have Praveen Patil. He's going to talk about portable science labs, and the project name is XPs. Yeah.
Hello. Good afternoon. After these wonderful sessions by these wonderful kids, I'm really very tense now. I'll just try to finish everything in 4 or 5 minutes. This is something about a wonderful kit that with which kids can do wonders, like the one which I have just experienced now. Unfortunately, this is the situation in our science education system. When you just think of what will happen to a vehicle which has these kind of wheels. One, that big wheel represents theory and the other one represents experiments. It doesn't go anywhere. Most of the times, science is taught from the textbook without giving importance to experiments and real understanding. And as a result, students fail to correlate their classroom experiences to the real life problems that they encounter in daily life. And to correct this, science learning through exploration and experimenting can be a good measure. But if you want to do that, providing affordable, low-cost apparatus, equipment to the students is a difficult thing. Say for example, if you want to do some simple experiments, very simple experiments like generating electrical signal and trying to plot it on a screen. So what are the things we need? We need a CRO, oscilloscope, that is a costly equipment. Students can't afford to have them at home, right? Okay, you need different sensors. Now what I'll try to do is I'll use this very simple kit and we'll try to fetch data from the hardware using a very simple Python code and we'll try to see what kind of signal we are generating. So what I basically have here is a simple DC motor. Maybe in the end I'll show you after disconnecting these things. We have a very simple DC motor, then a small neodymium magnet which you'll get in any toy shop, and a screwdriver. So using this, I'll create a simple pendulum-like thing. And then, okay, the thing is very simple. Okay, when we power this motor using a DC battery, that wheel starts rotating. And without connecting any power source, if I just rotate the wheel, power should be generated at the back end, right? So I'm doing that. I'm just connecting the magnet to the wheel, and I'll use this as a pendulum. Just a second, please. Okay, there is a small problem there. Okay, maybe I'll try something else first. Oh, this wire is disconnected. Okay, I'll just explain what exactly will happen. Maybe a little later I can show it to you because we do not have that time. So if I just move this, right, it's a pendulum. And the similar waveform, AC waveform will be generated, and that hardware can fetch the data, and with a simple Python code we can plot it. Okay, a very simple experiment that can be done with different instruments for studying sound waves. A concept called interference of sound is very difficult to demonstrate in a normal laboratory. So what we need is 2 sources of sound, and to have the input for those sources of sound we need frequency generators, function generators, and then to plot that we need a CRO. But that can be done very easily with this kit. Okay, what I am doing here is I have used 2 simple buzzers. Okay, they will generate the sound, and for activating the buzzers I am generating square waves here using the same kit, and I am using a simple mic here to connect the signal, and the output of the mic is actually connected to a CRO. There is a Python code for this CRO, and that will plot as a graph. Let's try. So I'll just connect one buzzer to one square wave generator, and I'll say start. It generates a sound. I hope it is audible, right? And then if I bring it very close to the mic, you can see that wave, right? Okay, you can change the frequency here, and you can see what exactly is the difference that is happening. So for kids, it's really wonderful to learn these things by self-exploration. Okay, let us test the other buzzer also, if it works. Yeah, so this is one more buzzer with slight difference in frequency. I'm using 3400, 500 and 3600. Okay, now what I'll do is Okay, what you saw here is continuous wave with same almost constant amplitude. If I start both the buzzers together, then you will be able to see something else. Right? This is what happens when two waves are traveling simultaneously in medium and they superpose. When they go in phase, you get larger amplitude. When they go out of phase, amplitude will be less. So like this, using this very simple instrument, many science, physics, electronics experiments can be done at home. So it's like having your own science lab in your pocket. And the code running behind this is from Python, and because of Python, the things have become very easy. For a person like me who has never undergone any training in computer science, never learned any programming, but within 2-3 days I could learn these simple things. And you people are from computer science background, if you know something about programming, you can do wonders with this. In fact, our dream was to provide a very much low-cost, affordable science laboratory to every student in the world. And now one student has helped us to develop Android app for this. So with your mobile phone and this, it has really become a science lab in your pocket. Thank you very much. Okay, 1 second for details. You can log into xpies.in, that is our main site, and project is developed by IUAC, Inter-University Accelerator Center, New Delhi. Thank you very much.
Thank you, Praveen. Next we have Shrivanti. She's going to talk about email classification.
Okay. It's on. It's on. Hello? It's audible. Okay. Sorry. My name is Shrivanti. Today from morning we were in open space talking about this. We had a lot of talk about this. I don't have something to demo from a lot of presentation were amazing, but this is just a gist of Gmail API and LDA topic model. I don't know how many of you know, but 2 months back in Google I/O, Google released Gmail API. So before this, all of us were using IMAPs to access our email server. So Gmail API is very handy, it is faster to access the mailbox. So that is one advantage. And one more is, I'm talking as LDA topic modeling. So we have a lot of machine learning algorithms. So LDA is something which we can use to classify the documents. So our problem is basically we are from travel industry. Most of the travel industry, the typical problem is they get a lot of requests through emails. So and for the operation team, it is always difficult to classify the mails. They don't know when is a booking request, which one is if somebody is following up or somebody is confirming the voucher or invoice mail. So these are the different categories we wanted to classify from our Gmail. So basically we wanted to group our mails. So why LDA? Because there are quite a number of classification algorithms, KNN, NIBs, support vector machine, many. But for us, we don't have time to label the data, and all of the data we had was text. So LDA was fitting well for our case. And coming to Gmail API, I would ask everyone to use this because it is really a cool thing they have done from past 2 months. I don't know how many of you know it. It is very handy to use. Just use your IDs. Usually it will be me when I'm going through my inbox, and you just have to give user ID, and using OAuth you just authenticate your app, and you can write code using any language, Python, Java, PHP, anything. So for us, we were tracking all the thread IDs, a mail, when a request came. So when a booking request is coming, and when it is turning into a booking, and whether it is dropped after giving us, after we give them some codes. So such things we were able to track with this. These are the key resources you can extract from Gmail API. You can extract the message text, you can take the labels, whether unread messages, read messages, and all that. And also you can track the history. So if you want to track only the latest mails from past 1 month or 2 months, something like that. And for LDA, we have Python implementation of LDA that is called Gensum. And for processing the text, we are using NLTK. So this is my crisp talk. I don't have something to demo. Thank you.
Thank you, Shrivanti. Next we have Ramesh. He's going to talk about Ansible.
Hello. I don't have slides. Okay, hi, I am Ramesh. I will be talking on Ansible. I don't have any slides, so I will be just going through the Ansible website. Ansible, how many of you know how many of you know Puppet? Okay. So Ansible is a simple IT automation tool which is built using Python. It doesn't need any client-side software to execute its playbook on the host. It simply uses SSH to connect to the host, or it uses OpenSSH, or you can use Python's Paramiko library to connect to the remote host. So using Ansible, you can do configuration management, you can do deployment, you can run ad hoc commands. You can also do testing using, simply you can do any automation using Ansible. So can you, okay. At the core of Ansible, there is something called modules. Ansible already comes preloaded with 200 plus modules, which are written in Python, core Python. But apart of Python, you can also use any language like C, Java, Ruby, even Bash. The only condition it should meet is it should emit JSON output. Unless and until you are giving JSON output, Ansible can accept any damn language whichever you want to use. So apart of module, so modules are the heart of the Ansible. So you include modules in the playbook. Playbook is a simple YAML file which contains task, and this task will execute your modules. So simple task file will look like this. So this is a task file. You are saying what all host you want to execute on. So this is a group name which we'll cover later. So these are the simple tasks. You give a human readable name for the task.
you specify the module. In this case, it's a yum, and you are saying it to install HTTP package, and its version should be latest. That's all. Just these 2 lines of code will actually install your HTTPD on your remote host using SSH. So for playbooks to execute, you need to tell him what all host to execute on. So Ansible relies upon an inventory file where you pass all your host. You can also pass your host groups on that. So you can directly pass the group name and it will run on all your hosts. It's again a simple INI file, which Windows uses. Apart of that, Ansible also provides some cool stuff called plugins. Plugins, it's a callback plugin. So whenever you execute a playbook, if you want to run a separate piece of code, like when a playbook executes, it finishes it completes its execution. You want to notify a group of people. So you can write an email, a short script which will email the output of the Ansible execution, and it will send a mail to the users you want to notify. Or you can add something like logging and other cool stuff. So it simply goes like you execute a Ansible task, you pass your playbook, and playbook will have your custom modules which will run those modules on the host which is specified in your host inventory, and it will give you the output. And depending on that, you can run your callback plugins which will again notify your users or do other cool stuff. Yeah, that's it. So one good thing about Ansible is it, compared to other configuration management tool like Puppet, Ceph, and Salt, it's like it doesn't need any agent, right? On the client side agent, it simply uses your OpenSSH or Paramiko, and you can also even have a pull-based setup where Ansible will pull all your playbooks from your Git repository directly. So you don't need to SSH it. You can set up a cron job, and it will pull your playbooks directly. Yeah, that's it. Thank you.
We have one more slot available. Is there anybody else who wants to give a lightning talk right now? Cool. Come.
Amazon. Shantanu. How to connect? How to use this? AWS.
So next we have Shantanu, who's going to talk about AWS.
How many of you have used Amazon Web Services? A lot of people are there. Boto? I'm just going to tell you something about Boto. First of all, some of the people who don't know about Amazon Web Services, this is how the screen look like when you log in, and this is how your S3 look like. S3 is a service where we store all our files. Redshift is for big data, and EC2 for all my servers. This is T1 macro, cheapest one, and this is N3 2 extra large, which is very costly. If you want to see the bill, you can also see the bill. Boto, now you can use the same interface to manage your web services, all this S3 and Redshift, but Boto is much more important. See, when you say import Boto, that module gets imported, and you can start working with your Amazon properties. Here what I am doing is that I am just giving access key and secret key so that I can connect to my account. Then I am creating 3 accounts: Redshift connection, EC2 connection, and S3 connection. So I am creating 3 connections using this Boto module, and these are the methods of Boto. So Boto.connect Redshift will connect me to the Redshift. Then I will use this connection object later on to create Redshift clusters. I will use EC3, EC2 connection module, connection object later on to create my servers, and S3 connection object for creating, uploading S3 files and downloading files and deleting the files. Just see how it is done. This is my, I will just first let me show you the EC2 things. List all reservations. So EC2 the EC2 connection that I just created, take that connection object, get all instances, will list all the instances. That is all the servers that I am already having. That is this list, the list of 3 servers. So what I am saying is that instead of going to my user interface, through programmatically I am managing my Amazon resources. First I import Boto, I give access key and secret key to connect to my account. I create an EC2 connection object, and then I say get all instances. To get all the instances, then I will get print reservation instances. So I will just print it. So just 3 lines and I get all the instances which I have. I can also get only instances, and I can also I can also create a new instance, create an image. I can create images. Start an instance is run instances is the method, and uses EC2 connection object and run instances. AMID is this AMID, the image that I want to base my EC2 instance on. So I am creating an instance just using 4 lines of code. I can create n number of servers. I can have ads, and I can configure that server as well. Whether I want it 6 GB, 4 GB, 8 GB, 64 GB. Amazon EC2 has n number of options. I can also manage my hard disks. I can manage attached volumes. I can terminate an instance. I can copy a file to S3, and I can delete a file from my S3 bucket. And Redshift, how many of you are using Redshift? Oh, quite a few. But Redshift is really a good option for database. If your MySQL is not scaling and you have a big data, really big data, use Redshift. And here how you can do it programmatically, check the active clusters, start a new cluster. All your Redshift can be managed like this. Just 4 lines of code and you can do anything in Amazon properties using Boto. Boto is extremely powerful. Use it, you will like it. Thanks.
Thank you, Shantanu. Next we have Ronaldo, who's going to show his project, which is known as Verbalizer.
Hello, am I audible? The girl, she talked about email classification. I am going to show a small demonstration of that using the name-based classifier. In Python, there is a module called a text blob. From that, I am importing the name-based classifier. Name-based classifier is a mathematical model for classifying lots of things, means not just text. Right now I am doing a project called Verbalizer. It uses natural language processing tools. In this, I am training the name-based classifier using a set of predefined sentences that I am planning in the future. For example, if you see this one, define car, this comes under the classification of definition. So, if the user use a query like, can you give me the definition for a car, it automatically gets classified under the classification definition. So, if you see here, the first example that I have given here, what's the time? Here, in the training data, I have given what is the time now. It is classified under the classification of time. So, the sentence I am giving now, the input sentence, it is analyzed, and based on the probability of the training data that I have given, it will classify automatically into that classification. For example, now it's automatically classified under weather. The most informative features, it shows how the classification is made and what are the probable features that the name-based classifier is looking for in that sentence. I am not having the exact sentence, what's the weather around here in the training data. I can't have that. I can't have.
But I think while we're waiting, I'll just quickly introduce the concept to you. And maybe a little fun way to do it would be with a little slide deck. So there's a panel discussion planned for tomorrow afternoon. It's at 2 o'clock. It's going to be a little panel debate style format, talking about 3 web frameworks: Flask, Django, and web.py. We'll have Kiran, Anand, and Arun, all of whom I think you guys might have seen speaking earlier today. Each of them will speak for make sense for you, and we'll try to cater to some of those questions around which framework makes the most sense if you're starting off trying to figure out where you should go, or if you're building a large application at scale, which framework might make more sense. And finally, also looking at the future, given a lot of the changes happening with the WebSocket subprotocol and async that's a part of Python, and impact on delayed jobs, and some of the futuristic things that we're looking at. So the way this panel tomorrow 3 is going to be structured, we'll cover 3 frameworks, we'll have 3 evangelists, there'll be 3 rounds of debate, and we'll have room for 3 audience questions. We'll let people post questions via Twitter, via the #PyCon India tag, and time permitting, we might pass around some slips of paper where people can fill in questions. We'll collect them up here and read them out. And just as a little fun thing, we're thinking we'll also try to get some feedback from people, courtesy a little missed call voting app. So this is just something fun that I threw together earlier this week. And the way this works is, okay, you go ahead and switch it over. Do me a favor, if you don't switch it, just bring up safraj.heroku app. Let's give you a URL. Yeah. I'll just do a code walkthrough with that. Connecting. Let's just load up. Meanwhile, I'll just quickly talk through this piece of code. So the way this is going to work is there's going to be 3 phone numbers here, and I'll explain what you'll need to do in just a minute. But the way this will work is, and some of you might already be familiar with missed call voting systems. There's at least a couple of companies that have offered that. But I'll let you guys just imagine that one of these is a choice here of picking Django, Flask, or web.py. Or maybe it's a question of picking Federer, Nadal, or Djokovic, or whatever you'd like to. Could be one of these choices. And you need to give a missed call to the number which represents your choice. And Grace here will bring up a page where your votes will get registered. You won't be charged for the missed call. It's just a missed call. But using some of the backend APIs which I'll leverage, the missed call data feed will come into me, which then I'm logging into the parse backend. So I'll just spend 2 minutes doing a quick code walkthrough since it's a lightning talk, not a lot of time. This is just a very simple Flask web app, which also uses parse.com's backend to keep things very simple. And I've got 3 routes that I've set up here based on 3 different phone numbers. And I'm treating each call that comes in as a little clap, essentially an endorsement of the speaker or the session that you liked. And I'm taking the feed here to grab the telephone number and saving that as a vote. I'm also just masking off your phone number details, which will get pulled up here. So you don't need to worry about your phone number getting shown to anyone else. And all this data will get deleted as well later on. So a very simple, straightforward app out here. Now, if you could flip this over, I'll just quickly show you guys. Okay, there's no way for me here to. Okay, let's switch it. Sorry about the confusion, guys. It's just Wi-Fi has somehow been down. Don't usually require 2 other people helping. So if I had network, this would be the backend where you could see that there's already a few people who have been helping me test it, and they voted against. You can see 2 people voted for choice 2, 3 people voted for choice 4, and 5 people had voted for choice number 1. Okay, and this is just built using Flask API. Now, what I'll request is I'm just going to bring up these phone numbers here. Actually, Chris, if you could just read those out to me, I'll just list these out here. Yeah, I'm just trying to see what the best. It's been a while since I've used Windows. So. Okay. 3075 26. And the others are just sequence, right? Okay. So this is option number 1. And then you've got 2, 3. So let's just say the first one is Roger Federer. Federer, pardon my typos. Let's say number 2 is Nadal. And the third one is Djokovic, who should have come to Bangalore but didn't. So I don't know if you guys can see the numbers here. Is it large enough? I'll just make this a little larger. And 48. Okay, here we go. Much better. So guys, now's your time to vote. So all you need to do is pick the player that you like the most and give a call to this any of the numbers here. Let it ring 3-4 times. It will automatically hang up. You don't need to hang up. Let it ring 3-4 times. The call will automatically drop. So just pick up your phone, dial this, depending on whom you're interested in. Okay. Let me just give people enough time to make their calls. And we can come in here and you can see it's 2, 4, and 5 were the previous counts earlier. I haven't flushed the DB in this case, but let me just refresh this now. 2, 4, and 5. Whoa! Someone's been helping here. We've got 24 against number 2. People love Federer. 18 here and 23 here. Those are some inordinate numbers. So let's see. I didn't actually keep count to see who jumped the most, but I think Federer has jumped the most because he was at 2. So so that's the main demo. I mean, I'll just refresh once more in case more people are voting. So that's the very simple demo of just missed call voting. It's a simple way where I'm hoping that maybe a system like this could be used for instant feedback at next year's PyCon. At the end of a session, people just are given 2 numbers or 3 numbers to call, and you call to say, hey, I like to talk, or no, I didn't like it. So that's the gist of it. That's all I had, and in questions if people do. So.
All right, thank you, Arvi. That was the last talk for Lightning Talk today, and we end the day for PyCon India 2014 today. Tomorrow morning, we start at 8 again. 9:30 is the first keynote, and 8 o'clock the breakfast and registrations begin. You will have to check with the registration desk tomorrow morning once again so that we mark you there, and we have a head count of how many people have turned up so that we can distribute the swag accordingly. Thank you for coming. See you tomorrow.